Welcome to the second theory lunch talk of the semester. Today we have Siddharth Bhandari, and he's going to tell us about perfect sampling of graph K colorings where K is larger than 3. So I'll give it to you.
All right. Thank you everyone for coming to the talk. And as the title says, I'm going to talk about perfect sampling of graph K colorings when K is more than 3 delta. We'll get into what these parameters mean. This is joint work with Sayantan Chakraborty at TIFR Mumbai. So I thought it would be a nice idea to start off with a puzzle because if you get bored during the talk, you should have something else to chew on other than the food. And actually this puzzle is going to be kind of important because it serves as a building block for our algorithm. So here's what the puzzle is. So we have our usual culprits Alice and Bob, and Alice is given as an input a subset S of K. So there is a universe of size K. This is what you should think of as the number of colors, but right now just think of it as an arbitrary set, and there is some parameter delta. So Alice gets as input a subset S with the promise that it's not the full set, okay? And Bob on the other hand receives an input which is a subset of K with the promise that it's also contained in S and its size is at most delta. So it's the usual communication complexity setup where Alice doesn't know Bob's input and Bob doesn't know Alice's input, and they have to communicate. So what do we want them to do? Well, Alice can use random coins. You can even assume the randomness is public, and she sends across a subset of K to Bob. And you can even assume the subset is ordered, but it really doesn't matter if you assume that the randomness is public because Bob can always figure out what Alice has done. But let's just assume that it's ordered. And what does Bob have to do now? After receiving L, Bob needs to flip some more coins, and he needs to output a sample from L minus T. Now for this to be sensible, you already need the condition that L minus T should be non-empty, right? And what do we want? We want that no matter what the inputs to Alice and Bob are, the distribution of the output of Bob, that is C, should be uniform over K minus T. So it should be uniform on the complement of the red set, right? But the constraint is that Bob can only output from L minus T. So, well, what is our goal here? Our goal is to minimize the size of L. Like how small can we set that list to be, all right? So here's a trivial solution that you can probably guess is already delta plus 1. That is, Alice just disregards whatever input she gets. She just randomly samples a set of size delta plus 1 and sends it to Bob. And Bob randomly samples a color from L minus T. It should be pretty clear that this distribution would be uniform on K minus T because we're not favoring any particular color this way, right? But the question is, can we decrease this size? All right, so keep this in mind, it will make an entry again. So let me just say what the problem statement is. We are given a graph G and of size n and max degree delta, and we have some set of colors K. And typically we will think of K as being larger than delta plus 1 due to ergodicity reasons. And we denote the set of proper colorings by script C. It's just the set of all proper colorings of the graph using K colors. And what we want to do is provide an expected polynomial time algorithm which terminates with some coloring. But notice that we need to produce a perfect sample which is uniform over script C. So that's what I want to highlight. This is not an approximate sampling problem. We need to produce a perfect sample. That's the difference. And what is our aim here? It's to obtain algorithms for as small a value of K as possible. That's generally the entire game in this field, even in case of approximate sampling. And I just wanted to point out that a naive accept reject algorithm where you just sample some coloring, it may not be proper by assigning colors to the nodes randomly. That won't work because it's easy to see that the ratio of the total number of colorings to the number of proper colorings will be like exponentially small in n, so the amount of time you end up taking will be too long. And what did we know prior to this work? Well, there was an algorithm dating back all the way to 98 by Huber which gave a delta square plus 2 delta bound on K. So he provided an algorithm which worked whenever K was larger than delta square plus 2 delta. Usually this largeness is measured in terms of the max degree, and this is the bound. And in this work we improve the bound to 3 times delta. So yeah, for delta equal to 1, I guess both are the same, but that's like not a very interesting case, but for larger delta this is better. So let's move on. So I just wanted to sort of say that this is going to be a Markov chain based algorithm. So what's the underlying Markov chain we are going to use? And if at any point like you're not comfortable with what I'm saying, please stop me and ask me. So it's the Glauber dynamics. I guess a lot of you already know what it is.
Can I ask a question?
Sure.
On the prior work, I thought that there were algorithms that were linear in delta.
Yeah, those are there for approximate sampling. I'll come to that. Those are all approximate sampling algorithms.
What does that mean?
That means that you're not required to produce a perfect sample. You can produce a sample which is within epsilon total variation of this distribution, like which is very close to the uniform distribution over C.
Okay.
Yeah, we require a perfect sample. That's important. Thank you for asking the question. We require a perfect sample.
So the traditional algorithm would be just to use a Markov chain, run it for some number of
Absolutely.
steps, and say, okay, I've done enough.
Yeah.
But it's not perfect. It's still got an epsilon which is going
It's to 0, but it's not 0.
exponentially possibly even to
Yeah.
0. But that's not good enough for you.
That's not good enough for me. Yeah, exactly. Yeah. Thanks for raising the point. It's very important that we are doing a perfect sample. Otherwise, we know much better bounds. So what's the Glauber dynamics? Its state space is the set of all proper colorings, and its stationary distribution would be the uniform distribution over C, which we are denoting as pi. And I just wanted to sort of recall what a step in this Markov chain looks like. So let's say you are at a particular coloring chi superscript I. This I is just denoting a time index. So how do you make a step? You choose a vertex in the graph at random, and you choose a color for the vertex out of the set of available colors. So this, if you just stare at this expression, you'll realize that this is nothing but the union of all the colors in the neighborhood of V. So the complement of that is the set of available colors at V. And we simply update the color at V to be a uniform choice from the set of available colors. And for all other vertices, we just copy the previous coloring. Yeah, I think this step, has anybody got any doubts about this step? This is like, I guess this is simple enough. And typically this is, as was being pointed out, you start with some state, let's say chi 0, it's a coloring, and you sort of apply this update, you get a new coloring, and so on. And that's how the Glauber dynamics evolves. And let me just come to approximate sampling now.
So you might want to say that since you have k is much more than delta, you can start with the coloring efficiency.
Yeah, that's a good point. Yeah, because k is like more than delta plus 1. Even if it was delta plus 1, you can always use a greedy algorithm to color the graph. So you can start with an efficient coloring, and you can use the Glauber dynamics. So how does the approximate sampling regime work? Well, you run some ergodic Markov chain for long enough, and you usually expect to mix towards the stationary distribution. And typically you use spectral properties or a coupling argument to show that the thing mixes, right? And that's the point that was being mentioned, that the running time is generally proportional to the log of 1 over epsilon, where epsilon is the total variation between the target distribution, which is the stationary distribution of the chain, and the distribution you will output. So, but this is not good enough for us because we need to set epsilon to be 0, right? I just wanted to mention that approximate sampling has received a lot of attention, and there's been a long line of work. This is just some of the results, starting with Jerem, who showed that the Glauber dynamics mixes for 2 delta, and then Bubbly and Dyer basically gave a simpler proof of this using path coupling. This was a breakthrough paper where Vigoda showed 11/6 delta, and recently it's been improved even further. So moving on, let's go to a perfect sampling paradigm. That's the one we will be interested in. So there are various methods to achieve a perfect sample using a Markov chain, but the one we will be interested in is called coupling from the past. And this was a breakthrough paper of Propp and Wilson in '96. And but it turns out that these kind of ideas were already present in the work of Lorenz in like all the way back in '62. And the claim to fame of this Propp-Wilson paper was the fact that they were able to sample from the Ising model on a huge lattice grid at the critical value. So it's okay if you do not know what that is, but I just wanted to sort of convince you by hand waving that it's an important line of work. So let's get to what coupling from the past is. So we are given an ergodic Markov chain P with some stationary distribution. You can keep in mind the Glauber dynamics with the stationary distribution as pi. And what we want to do is use this Markov chain somehow to get a perfect sample according to pi. So this is one natural attempt. Let me explain what is going on. So you have this state space S of the Markov chain, and what we really want to do is we want to sort of start a Markov chain at every state of the state space and evolve it in a manner which respects p. So what do I mean by that? Let's just concentrate on the transition from t equal to 0 to t equal to 1. So what is tau 0? Tau 0 is just a distribution over the set of functions from the state space to the state space. So basically it's telling you, if you are at this state, it's a random variable which will tell you what's your next state, and it's the same thing for every state. But what's the requirement that we need? It's not an arbitrary distribution, it's a distribution which respects p in the following way, that no matter which state you take over here, and if you just look at the marginal of tau 0s, it will be the transitions that you will get will be according to the Markov chain P. So we respect the Markov. So if you track the trajectory of any particular state throughout this algorithm, you will see that it has evolved according to the Markov chain P. Now it's not that every state is evolving independently, because that is something which is prescribed by tau 0. It's just that the marginal on every state is correct. I hope this is clear. And we evolve all the chains here, the modest chains, and we hope that at some point, if the coupling rule P is sort of good enough, eventually we will observe that all the chains have reached the same state S star. And what do I mean by sticky here? Sticky just refers to the fact that if two Markov chains sort of coalesce, that is, if two states reach the same state in one transition, then they always stay the same. But that is sort of inbuilt here, because what tau i's are just functions. I mean, are there any questions about this? Something unclear? I guess this is clear. So one natural attempt is just to wait until we see coalescence, and let's say gamma is the stopping time when we observe coalescence for the first time, and then we just output the state S star. It looks natural, but the thing is, can we do it? And it turns out you cannot, because here is an example where this won't work. It's a very simple Markov chain, two states. It's easy to see that the stationary distribution here is going to put 2/3 mass on A1 and 1/3 mass on A2, just detail balance. And what's the problem here? The problem here is, if you were to run this algorithm, you would have realized that you would always output the state A1, because whenever you have two states, in one transition, A2 will always land you to A1. So the only way you can really coalesce is if A2 goes to A1 and A1 stays on itself, right? So this is not according to the stationary distribution. So the answer is you cannot do this. So all right, but let's try to see why the previous algorithm doesn't work, which will sort of tell us why the CFTP is such a clever idea.
I
Sorry.
don't understand why you're showing you going to state S star.
So S star is, sorry?
Well, you're saying that.
I'm saying that we sort of run all the Markov chains starting from each state in S, and we wait until we see that there is only, until all the Markov chains have coalesced to a single state S star.
Oh, I see. So you're running this Glauber algorithm.
Yeah.
For every single state.
Yes.
You're running it forward in time.
Yes. I'm running it forward in time.
Like Chinese last names. The number of last names keep decreasing as you go on, right? It's like,
yeah, that way.
that's a bad example.
Yeah, that's right. So we basically, yeah. So we have these modest many Markov chains. Each is evolving in a way which respects the transition matrix P or the Glauber dynamics, and at some point we will observe that all the Markov chains have hit one single state, that is, they have coalesced, and we want to output that state, but it turns out that this is not a correct algorithm, and here's a counterexample for that, because in this Markov chain, whenever you coalesce, you have to be at A1, but the stationary distribution puts 1/3 mass on A2, so it's not correct. So yeah, I wanted to find out why doesn't the previous algorithm work. So let's try to do an attempted coupling proof, because coupling proofs are generally slippery. So, but in this case, we already know that we are going to fall. So let's see. So yeah, let me just put it up. So we have this this evolution of the mod S Markov chains that we just talked about, and let's consider a ghost chain. So the name, I call it a ghost chain because it's not really, it's just a chain you use for a proof. It's not really run. So let's say that there is some ghost chain which has time t equal to 0, declares its starting state to be S0, which is distributed according to the stationary distribution mu. In particular, it's this one. And then it just copies the transition you have put out, right? So because of this rule that I was mentioning, that tau 0 respects the Markov chain, you know that the ghost chain has evolved according to the matrix P, or the Glauber dynamics in our case. So this statement is correct, that no matter which time you look at, and you look at the state in which the ghost chain resides at time t, that distribution of this random variable will be according to the stationary distribution mu, because we are evolving a Markov chain starting at the stationary distribution mu, so all the distributions stay mu. And therefore we would like to conclude that the output state S star is mu. Of course, the point is that we do not know what S0 is, because as this is just a ghost chain, we don't know what it samples, and but the thing is, we definitely know that at t equal to gamma, the ghost chain reaches S star, because all the chains have coalesced, right? That's what our algorithm was doing. But the problem with this argument is that gamma is not a fixed stopping time, it's random. So it's not correct to say that S star is distributed according to mu. Had it been a fixed time, that would have been fine. That's the problem. So here's a remedy. We can always sort of take a large enough time, capital T, and fix it and run the chains only to capital T. Now we have a fixed stopping time, so that problem should go away, right? But then there is a new problem. What if the chains haven't coalesced by that time, right? Unless we make t equal to infinity. Now this sounds nonsensical, so what do we do now? So we'll do something even more nonsensical, which is we'll make t equal to minus infinity. So I'll get to it in a moment, what do I mean by that. But this is why the name coupling from the past comes, because you sort of think of time as going from the past to the present instead of like present to the future. That's why you get the name coupling from the past. So let's just try to sort of be a little more concrete about what we are saying. So imagine we are running a Markov chain from every state, starting at t equal to minus infinity. I know it doesn't make sense right now, but just imagine that. T equal to minus infinity to t equal to 0. And if our Markov chain is ergodic, which we assume, and our coupling rule is reasonable, we can say that, you know, with probability 1, all the chains would have coalesced to some state at time t equal to 0, because they've got an infinite time to run. They started at minus infinity and they ran till 0. So with probability 1, they should have coalesced. But that's the question still remains, how do we run them from t equal to minus infinity? But the answer is right here in the second point. That is, we do not need to run the chains from t equal to minus infinity. We only need to determine the state at which they would have coalesced, right? So that's the algorithm. That's the coupling from the past algorithm. And but I'll give more details in the next slide. Are there any questions at this point? So so let's just assume we have a decreasing sequence of integers 0, n1, n2. You can even just think about them as being 0, minus 1, minus 2.
Can I ask you a question?
Sure.
Are you saying that for all the different states you might end up with when they coalesce,
Yeah.
there's some probability distribution over which state you will coalesce in?
Yes. That probability
But
distribution.
is that what you're trying to compute?
Yes, that's what I'm trying to compute.
That's the exact.
That's the exact, that state would be exactly the correct distribution. In a moment I'll give the proof of why that is, but the intuitive argument is that
Didn't you just refute that though a minute ago?
no, what I refuted in a minute ago was the fact that if you output this state, which is at a random time, that won't be the correct distribution.
Oh.
But now we are always outputting that state at a fixed time. It's as if
Okay, I see.
we ran the chains a little bit further to a large enough time and then output that
I see.
distribution,
Okay.
right? But I'll give a proper, this is all very hand wavy, and sorry, where was I? Yeah, so let's just look at the algorithm once, and then we will also sort of look at a better proof. So what do we have? So now since we are going to index time by negative numbers, we have these distributions which are like tau minus 1 and tau minus 2 instead of tau 0 and tau 1. These are just the rules to evolve the chains which respect the underlying Markov chain, which is the Glauber dynamics, let's say. And you just sample some evolution or some way to evolve the chains according to this distribution. So what does the coupling from the past algorithm do? It sort of finds the first index I such that if you were to run the modest chains starting from t equal to ni to t equal to 0, notice that ni is a negative number here, the chains would coalesce to a particular state. Or in other words, the image of the composition of these functions, because these are functions from state space to state space, so all you are saying that the image of the composition of these functions becomes an image of size 1, right? And notice that this is all the algo does. It just samples from here and it finds the first index I such that the composition of this function leads to an image of size 1. Okay. Now already, I mean, you can ask me like what happened to the fact that we were supposed to evolve the chains from t equal to minus infinity to 0. But you can see that it really doesn't matter what the chains did in time prior to ni, because no matter what the chains did, they would all reach the state S star. Right? That should be clear, because what is the worst that can happen? That when you reach the time t equal to ni and you look at where all the chains have landed, they still have the entire state space, as in the uncertainty is maximum. There is one chain which leads to some state here for each of these states. That's the worst case. But even then, they would all coalesce to S star, and that's what we wanted to do. And this should sort of hint that S star is the correct output, like is the output according to the correct distribution. But yeah, this is all very hand wavy, and I can wave my hands as much as I want, but it's not going to make me fly. That's a quote I read in one algebraic geometric book. But anyways, now let's go into a little bit more of a concrete proof. So we'll just try to replicate the proof we were earlier trying to give, which was incorrect, but this time it will be correct. So let's just say that you want to show that the output distribution, that is S star, is actually epsilon close for any arbitrary epsilon to the target distribution, which is mu, right? And then you can obviously choose epsilon to be arbitrarily small, so the target distribution is mu. So we'll choose some time t large enough such that we observe coalescence of the chains run from time t equal to minus t to t equal to 0. This probability obviously depends on what your coupling rule is, like how are you evolving the chains. That is what will determine the probability. But if it's a reasonable way of evolving the chains, you expect to be able to do this. And let's say we have done this. Now I want to say that actually this already shows you that the output state S star and the target state in total variation are less than epsilon because of this fact. So let's see why this is true. Why is it the case that S star will equal, sorry, I wanted to say S prime here, I missed a prime. So there is an S prime here. So what is S prime? So S prime is like the state of the ghost chain. So we have a ghost chain again which will start at t equal to minus t by sampling an initial state which will be distributed according to mu. With 1 minus epsilon probability, we know the chains coalesce. So we will so the output of the ghost chain at time t equal to 0 will be S star, and there is an epsilon probability that the chains would have not coalesced, and the ghost chain can output something which is like S prime, which is different from S star, right? Because you do not know, because what we output in our algorithm is S star. We do not output S prime. We look for the first time, let's say like Ni, where all the chains coalesce, and then output the state at t equal to 0. Yeah?
Sorry, I think I forgot. Was mu the uniform distribution?
Mu is the stationary distribution of the Markov chain. Yeah, it's the uniform distribution.
Also, yeah, that brings me to another point. So the Glauber dynamics, are they constant degree? Because I guess you want to say that the stationary distribution is the uniform distribution.
So it's not necessary. So you can have graphs of non-constant degree, but the stationary distribution will still be.
It is still the case.
It will still be uniform because of detailed balance. Like you can just check across.
I see.
So where was I? So yeah, so there is a 1 minus epsilon probability that the ghost chain will actually, the state of the ghost chain at t equal to 0 will be S star, and with the remaining probability it will be S prime. One thing is clear, that this distribution of S prime is mu, because we have just evolved a ghost chain from a fixed time to a fixed time according to the Markov chain. And this is a coupling which shows that S star will equal S with probability 1 minus epsilon. This 1 minus epsilon comes whenever we observe coalescence, right? So this, just by this duality of total variation and coupling, this statement sort of makes sense now, right? Because you have demonstrated a joint distribution between S star and S, where S star equals S with probability larger than 1 minus epsilon, so the total variation cannot be larger than epsilon. But one thing to note is that, the important thing to note here is that, it doesn't matter where you start here, like where your algorithm starts trying to find the coalescence from. It would always output S star. That is because for all you know, N1 could have been right here, somewhere here, and your algorithm found coalescence at t equal to N1 itself. But that doesn't matter, because it will all have to go to S star. Because this is just by the nature of the algorithm, because even if you were to sort of, let's just assume that at t equal to ni, the chains have coalesced at S star by t equal to 0. Now if you go one step back in time and you run the algorithm again, it would still output S star. It's not that it's going to output something different, right? That's an important point here. But yeah, I hope it's somewhat clear what's happening and why this works. But I want to sort of,
So
yeah.
is it because you're saying that, look, S star is going to be reached with probability like 1 minus epsilon?
Yeah.
So if you go, you won't reach that if you go further back, and if you coalesce, you can't coalesce to anything else, because 1 minus epsilon of the mass is there. But 1 minus epsilon of the mass can't be at some other location.
No, sorry. So that's, I see, but that's not what I'm trying to say. I understand what you're saying, but what I'm trying to say is that, sorry, where did it go? Yeah, so what I'm trying to say is that, so let's say that this is some minus 100, where you know that there is going to be coalescence with probability, with good probability. Now your algorithm finds an index I such that when it runs all the Markov chains from t equal to ni, and it evolves them till t equal to 0, it observes coalescence. What I'm trying to say is that it really doesn't matter, even if your algorithm say was wasteful and did not, maybe checked it at ni plus 1, so it made one extra step, right? It doesn't matter, because it would still be outputting S star. That's simply because of the fact that the chains have coalesced to S star, right?
Right, and this is in contrast to the other case, right, where if you did an extra step on the right, it would change.
Yeah, that's a very good point. Yeah, this is in contrast to the, yeah, I think it's very difficult to go back, but yeah, that's right. In the earlier false algorithm where we were stopping at gamma, if we would have let the chain evolve for one step longer, the output distribution changes. Here the good thing is, if you let the chain evolve for one step further back, it doesn't matter, you'll still output S star. That's why it's a very clever algorithm, yeah. So, but I still want to sort of caution you, sorry, yeah.
When you say like t equals negative 100, you're saying that it coalesces with the probability at t equals negative 100, but that you mean over the choice of I fixed t, now what's the probability that it had coalesced from negative 100 to 0?
That's right.
But then when you say that when you fix this n, or whatever n was before, you're saying, okay, now n is actually a value that it has coalesced by, so you're not fixing n and then running the change. You're saying n is a value that it has coalesced by, so
yes.
to the left, because we run it 10, so it's going to coalesce after that.
That's right, that's correct. You got it right.
Just to double check, in this entire proof, the ren, this is over the choice of the FIs?
Yes, that's true. That's true. The randomness is over the choice of the FIs, which are sampled according to this product distribution of the taus. So
usually in coupling you use the same tau for each step, right? But here it's
yeah, here you don't need to. Usually it's the same, but in fact we will not use the same ones in the algorithm. But usually in this kind of algorithms you use the same tau. So so I just wanted to sort of say, that although these things are sort of, you can convince yourself whichever way you plan to convince yourself, but there are some interesting quotes I found out of this very nice book by Haggstrom, where he tries to point out that the Propp-Wilson algorithm looks very simple, but it was not discovered. I mean, it took some time to discover it, and the reason is because all the other natural variants that you try, which you think might work, actually do not end up working. I think this one we saw, this is just trying to say that, why don't I just stop at the first time I observe coalescence. And what this is trying to say is, so sort of I presented it in a different way, so this doesn't sort of gel with my notation, but what this is trying to say is that, you know, when your algorithm looks for the first index I, says that from t equal to ni to t equal to 0 it observes coalescence, but what if it doesn't? Suppose it doesn't observe coalescence at t equal to n1, so it will have to go to t equal to n2. So it will now need to sample fn2, fn2 plus 1 and so on, but the thing is it has to reuse the things it has just sampled at fn1 plus 1, because here we sort of pretended that, you know, you have an infinite sample which you stick to at the end of the day, but you obviously don't do that. You use them as you need them, but it's sort of not read once randomness. You need to store the random transitions you have made, because if you do not coalesce from t equal to n1 to t equal to 0, you'll have to go back to t equal to n2 and check whether for that particular sample did I observe coalescence. So it's kind of a subtle point, and I mean it's interesting to think about it, but I mean right now I'll just leave you with this, that it took a long time to fix this, by the way. It took 4 good years with a lot of false proofs until Wilson in 2000 gave a read once randomness algorithm for coupling from the past. So yeah.
Good question. So the state space is exponentially sized, so it's not clear right away.
Yeah, absolutely. Yeah. So what's the point of all this, right? The state space is still exponential for colorings. It doesn't lead to a good algorithm. But on top of that, you also need your coupling rule to be such that you actually can observe coalescence in polynomial time, because otherwise if it's no point. So we need both these conditions. Sometimes we have a property called monotonicity of the chain to help us. I'm not going to go into great detail because we are going to study something more general, which is called bounding chains, but just to sort of give you a flavor, you usually have some partial order or total order on S, and this joint evolution rule script P, it respects the partial order in the sense that if some state is larger than some other state, then even if you apply the function that you have sampled, fx would still stay greater than fy. It is pretty clear that you then only need to keep track of the maximal and minimal chains, because whenever the maximal and minimal chains coalesce, everything in between also has to coalesce due to monotonicity. And but we are going to study something more general, so I won't spend more time on this. So what we are going to study and what we are going to use for our algorithm is something called bounding chains. So this again tries to address the issue that mod has, that we have to run state space many chains. So that could be exponentially many. And this technique was discovered basically used by Huber in his paper where he gave the delta square plus 2 delta bound. And it was also independently used by Haggstrom and Nelander in 1999. So it provides a more general way to deal with Markov chains, that is even a broader class than monotone and anti-monotone systems. It's fine. I mean, we don't need to know what they are right now. So let's try to see what the bounding chain approach is. So let's just focus on the particular case of graph coloring, where our Markov chain P, the underlying Markov chain, is again Glauber dynamics, and the uniform distribution is the stationary distribution, right? And again, so this is a good point for those who have sort of lost me to sort of come back in, like board the flight again, because we'll pretty much just recap what we had done in CFTP. So we have this joint evolution rule that we discussed, which respects the Markov chain P, and let's just focus on the evolution of the CFTP algorithm from t equal to n1 to t equal to 0. So you would again sort of run all these many chains and hope to observe coalescence at some point, and we also consider this ghost chain which starts at S0 which is distributed according to mu, and its output is S prime, and we know S prime is distributed according to mu. The real problem is that we do not know S0. That's the biggest problem. We do not know what S0 is, and hence we are not sure if we know S prime. If we knew S prime, we could have just output S prime, because by definition S prime is distributed according to mu, as S0 is distributed according to mu and mu is stationary. But one way to determine S prime is that you can directly observe the coalescence of all these chains to a particular state, and then you can be sure that yes, that state to which they have coalesced is S prime. What the bounding chain does is it offers another way of establishing this coalescence, and by acting as an upper bound on the possible states of the ghost chain. So I'll make it more clear what it means, but it's just another approach to try to capture the coalescence of these many chains rather than running them individually. That's what it tries to do. So let's just understand what the bounding chain is. It's a chain with its state space being 2 to the k to the v. So at any particular time t, the bounding chain would prescribe a list of colors to every vertex. That's what its state space is, right? It's the power set of k to the v. So at every vertex v, you will see a subset of colors prescribed by the bounding chain. And let's look at this diagram to understand better what is happening. So the bounding chain will evolve with the ghost chain in a coupled manner. So, or rather I should say the ghost chain evolves with the bounding chain in a coupled manner, because the ghost chain never really evolve. We never really run the ghost chain. So so let's say that, oh yeah, I forgot. So what is the point of the bounding chain? So it maintains this upper bound property, that it says that no matter which time you look at and which vertex you look at, whatever is the color of the vertex according to the ghost chain is contained in the list of colors prescribed by the bounding chain. So it sort of captures all the uncertainty at time t in the ghost chain, right? So let's just take an example. Let's say that you have a particular graph, we had this input graph G, and let's say that at time t equal to n1, this state S0, which is a coloring, looks something like this. The bounding chain at this time would have prescribed lists to to each of these vertices, and because of this upper bound property, we know that the color green has to be somewhere in the list, this color yellow has to be somewhere in the list, right? And then when we evolve S0 to some state, let's say S double prime, maybe some color, like this green color became a yellow, then the bounding chain has to accommodate for that. And we'll keep on evolving it all the way up to t equal to 0. And if it so happens that at S prime, that is when we reach t equal to 0, we see that the list sizes prescribed by the bounding chain at every vertex have become a list of size 1, right? That would be really good, because then we know S prime exactly because of this upper bound property. We know that the ghost chain always has to take a color from the list prescribed by the bounding chain, and in particular at time t equal to 0, there is only one color at every vertex, so you know exactly the coloring S prime, which is what you want to output. So just to recap again, since we do not know,
Bounding chain maintain a set of colors at every vertex?
Yeah, the bounding chain maintains a set of colors at every vertex. It prescribes a list of colors to every vertex at every time.
Okay, so why did you draw the colors on the nodes of that graph then?
So this is the state S0. So S0 is a coloring, right? Our state space is the space of all proper colorings.
Okay.
So S0 is a coloring, and the bounding chain sort of captures all the uncertainty in that coloring at that point, as in
the bounding chain would have to have 5 lists, right?
Yeah, of course. There
in that graph, but you only wrote 2 of them there, right?
That's true. Yeah, I have just described 2 lists, but there are 5 lists.
Okay.
That's true. For every vertex v, there is a list, and what it is trying to do is capture all the what we do not know about the ghost chain at time t. So since we do not know the starting state, we don't have much of an option but to start the bounding chain in the maximal state, that is k to the v. I mean, every vertex has the entire set of colors available to it. But somehow, suppose we know that at t equal to 0, this is what I was saying, that all the list sizes have become 1, then we know S prime completely because of this upper bound property, right? In fact, if you think about it a little bit, what this property means is that all the chains, if you would have run the usual CFTP algorithm from all the chains, they would have coalesced to S prime. This is simply because you have not used any knowledge of S0. S0 could have been potentially any of the states, assuming mu has full support, S0 could have been any of these states. So all of these states have to coalesce to the single state S prime because of the upper bound property. But in any case, what we really care for is that the list sizes of all vertices by time 0 become 1, because then we can output S prime, which we know is distributed according to the stationary distribution. So yeah, but of course the point is that you need to design this coupling between the bounding chain and the ghost chain, which I have denoted by script J, such that the upper bound property is maintained and the bounding chain coalesces quickly. So you get an algorithm. So So yeah, so again, I mean, I'm sure I would have lost many of you, but this is like the template which will be sort of enough for the next part of the talk.
Does
So
the bounding chain have a rule, update rule?
yeah,
State?
yes, it does.
Okay, I guess I missed that.
That's prescribed by this coupling rule script. I mean, we have to design that rule. That's the algorithm. How you actually evolve the bounding chain is the algorithm.
You haven't done that yet.
You haven't given that yet?
Yeah, I haven't given that yet. That's the next part. So so this is how the template would look like. This is how the template of our algorithm would look like. So we will have some decreasing sequence of integers, in particular -t, -2t, -3t, and so on. And with t, we will set later to be poly in Kn. And we will specify this evolution rule script j, which you were talking about, with the property that, if you start at any ni with the bounding chain being in the maximal state, and you run the bounding chain for t steps, the probability that you will observe coalescence. So notice that running it for t steps is just going to the next block. The probability that you will observe coalescence will be at least half. That's what we will demand. Suppose we are able to come up with some rule j, then what our algorithm will do is it will go and find the first index I, such that if you start a bounding chain at ni with the full state, you will have coalescence at t equal to n minus I. That is, just by running it for t steps, I observe coalescence. If I observe coalescence at a time prior to 0, this obviously means there is coalescence at time t equal to 0. So what do we output finally? But this is something which we should be careful about. So let's say that the state at which the bounding chain coalesces is S tilde. We do not output S tilde because that's not what what the CFTP algorithm asks. The CFTP algorithm requires you to output the state at t equal to 0. But from here onwards, your life is easy. You just sort of sample these other you already have these other, you already know how to evolve the chain from ni minus 1 to minus 1. So you just simply evolve the state S tilde that you have obtained according to these rules and output whatever is the output of these this functional composition. So I have missed I should have applied this function on S tilde, which I have missed here. So I'm just saying that once you have obtained a state S tilde, which is the state to which the bounding chains have coalesced, you can sort of now evolve this chain all the way up, evolve this state all the way up to t equal to 0 and output that, because that's what the CFTP algorithm demanded. So it's clear because of this probability rule that the expected value of this index I will be at most 2, and it will overall, each of these steps are polynomials, so you'll get a polynomial time algorithm on expectation. So in fact, the way we describe j will be periodic with t. So every t steps, it's the same update rule that you will use. In the sense, its description is the same. So we'll only focus on describing j between -t and 0, because that will sort of complete the entire description, right? So yeah.
Is there a reason you describe it in this way where you do each integral separately instead of just working backwards until you have coalescence?
The reason, I mean, it's just more convenient actually. You could have done, it's convenient because of the fact that let's say you are t equal to n1 and you have run all the chains from t equal to n2 to t equal to n1. You have not observed coalescence, but possibly a smaller smaller number of states arises, like 2 or 3. And you want to say that, oh, now I really care for these 3 states coalescing. But this is not very easy to handle. I mean, the way the analysis goes is it just again assumes that, oh, at t equal to, so that's why.
So it's just for the length of the proof.
That's right. Yeah. It's just for ease of writing. I mean, it's just easier to analyze it that way. Okay. So I'm going to present Huber's bounding chain in a slightly modified manner. So what Huber suggested is we do the following. So remember, we want to couple the ghost chain and the bounding chain in such a way that we coalesce in t steps with probability at least half. So what Huber suggested is that you take your bounding chain at -t to be the full, to have the full states k to the v, and you do a warm up for n steps where you sort of just order the vertices in some order, and for each of these vertices you choose a list L of size delta plus 1. That's what the bounding chain will do. It will choose a list L of size delta plus 1 and some permutation of colors uniformly at random, and it will just update itself at time t plus I at the vertex vi to be this list L. Okay, so it's sort of going over the vertices, and to each vertex it's prescribing a list of size delta plus 1. And notice that we are only supposed to evolve the bounding chain, but we'll mention what the ghost chain does so that we get a coupling proof together with it. So what it does is it really chooses the first available color it has in L according to sigma. So it looks at the permutation sigma, orders the colors of L according to sigma, and finds the first color which it can use. Let's say that's C. So clearly it should be pretty clear that, and it updates itself according to C, and it should be clear right now that at least the upper bound invariant is maintained, that the ghost chain, the color of the ghost chain is always trapped in the list prescribed by the bounding chain, right? But this should already sort of start reminding you of the puzzle that we talked about. And after the warm up, it's clear that all the, sorry, this is at t plus n. After the warm up, the state of the bounding chain at every vertex is a list of size delta plus 1, right? So this is the warm up, and it's okay. Yeah, this is another thing I did not sort of mention, but it should be also clear that the ghost chain is evolving according to the Glauber dynamics, because overall the distribution of C is uniform over k minus t. There is no color in k minus t which is favored by this sampling procedure, right? Because this L is just arbitrary. So it's a completely random choice of size delta plus 1. So that's the warm-up phase of Huber's algorithm. So to describe the next part, I'll just need some definitions, so bear with me here. So a vertex V is good for us at time t if the list prescribed by the bounding chain is of size 1, right? Because this is what we really want. We want all vertices to have lists of size 1. And let's just denote by Wt to be the set of good vertices at time t. So just in a diagrammatically, you have the set of colors k, and at any vertex at time t, you have what do you know? So there are some you already have some estimate given by this red set of what the bounding chain knows about the ghost chains. So it's just the union of the colors in the list of neighbors of V prescribed by the bounding chain. You are trying to update the vertex V. It would have been great if you knew this blue set. This blue set is exactly what the ghost chain wants to avoid. It's the union of colors occupied by the neighbors of V prescribed by the ghost chain. But this unfortunately is not known to the bounding chain. What S is its best estimate for T, right? It knows that T is a subset of S, so and S is just the union of colors in the list of neighbors of V. So it should be clear that T will be a subset of S because of the upper bound property, right? Whatever color the ghost chain sees as blocked, the bounding chain will also see it as blocked. And what is this small set G inside T? Well, this is another piece of information that the bounding chain has. It's all those neighbors of V which are good, and you take the union of colors present in that. So these are colors which the bounding chain for sure knows that the ghost chain cannot use because they are block colors. For other colors, that is, it doesn't know T. So for all the other colors in S minus G, there is a possibility you might use them, you might not use them. That is, they might be available to the ghost chain, they might not be available to the ghost chain. For colors outside S, definitely the ghost chain can use it because the set of block colors resides inside S by our upper bound property. So moving on. So what do you do for the remaining time interval after the warm-up phase? You pick any vertex V uniformly at random, and you sort of pick a list L from K minus G. So for now you can even pretend to think of G as the empty set, but you sort of don't want to take a list which includes G because you know that the ghost chain can never use G, of size delta plus 1, and you pick some permutation uniformly at random. So let me just explain what is going on here. So what does the bounding chain do after doing this? It sort of looks at the first color in sigma, right? First color according to sigma in L. So this is this case A. Let's say it's C1. If it knows that C1 is outside S, it knows that the ghost chain will also use C1, because what is the ghost chain? So this is what the ghost chain does. It takes a color C which is the first available color to it in L according to sigma. So it takes the first color in L minus T according to sigma. That's what the ghost chain is doing, right? And it simply updates itself according to C, and we know that this is fine because the ghost chain evolves according to the Glauber dynamics. But what does the bounding chain do? What does the bounding chain do? It's slightly clever. Here it will sort of see that if C1, that is the first color in L, is already outside S, it knows that this is the color the ghost chain would have used. So it sort of updates its list to be just a singleton, because it knows that the upper bound property is going to be maintained, that C, the color used by the ghost chain, is going to be C1. In the other case, it doesn't know what might happen, so it just gives up and puts the entire L as its estimate for what the ghost chain will use. But and in the other case, when this doesn't happen, it is still possible that the ghost chain ends up using C1, like in this case, because the bounding chain cannot really guess whether C1 is something the ghost chain can use. But if C1 is outside T, that is, it is inside the set S minus T, the ghost chain is fine to use C1. But if C1 is inside T, then the ghost chain uses a completely different color, which is the first one in L it finds outside, right? So this is what the bounding chain does. Yeah, it's sort of like a lot of things going on, but this is not very complicated. It's just a neat and simple update rule where you can see that the ghost chain is always evolving according to the Glauber dynamics. The only good thing about this rule is, why is it any different from the warm-up rule? Because it gives you a chance of producing lists of size 1. In the warm-up rule, you are always producing lists of size delta plus 1, and eventually you want coalescence. So you need this probability to be good. And that's exactly what we will now sort of point out. What is the probability that our bounding chain at V produces a list of size 1? Well, this is a simple calculation. It's just the fact that the first color that you are sampling should reside in this band, which is K minus S. And you sample from a space which is K minus G, right? So, so this is the probability that you need. But is this probability going to be, sorry, what have I done? Yeah, is this probability ever going to be non-zero? If this probability is 0 for some reason, because it's quite possible that S happens to be the full set K, it might be possible that there's, so especially like during the warm-up phase, you see a list of size delta plus 1 ascribed to every vertex, each of your neighbors. Then S is the set of all blocked colors according to the bounding chain, and this could be the entire universe K, in which case this is just going to be 0, because it will become K minus K. But if you always ensure that K is larger than delta square plus delta, you notice that this is always a non-trivial probability, because S can never equal the full set, right? And this is what our case A was in the previous argument. So this is the probability we are really after. So recall that we have defined WT to be the set of good vertices at time t, that is those vertices which have list size 1. And our condition for coalescence was that at time 0, the set of good vertices is the entire set, all the vertices are good. So we want this. We want to say that probability that W0 will equal n is at least half. This was what I mentioned in the template, that you want to describe a coupling rule where for each block there is more than half probability of coalescence. And what Huber did is he analyzed the drift of this random variable mod WT and showed that, so this is already clear that you need delta square plus delta simply because otherwise you will not even have non-trivial probability of producing lists of size 1. And showed that if you sort of give him an extra delta, he is able to show that in expected polynomial time this WT will go and hit the condition of W0 being n, right? So this is what Huber showed, and for that he needed the bound delta square plus 2 delta. But what is the bottleneck for improving the bound on K in this approach? Well, it's an all or nothing approach. As we saw in the algorithm, either the bounding chain is very happy because it has observed this color C1 outside S, which it can use. It definitely knows that the ghost chain is going to use C1, or it just gives up and produces a list of size delta plus 1. It's not being very clever about the knowledge of other lists at its neighbors. So that's one bottleneck for improving the bound on K. But sort of now let's come back to our puzzle that we started with. By now it should be pretty clear that what role is being played by whom. So suppose we want to update a vertex V at time t. I'll sort of describe the puzzle again, but let's just think of the bounding chain as Alice and the ghost chain as Bob. So the Alice and Bob in our puzzle now have the roles of the bounding chain and the ghost chain. And what is the message from Alice? Well, it is the list L that the bounding chain has been using. This is also what I wrote for the puzzle. I'll just bring that puzzle forward again. And STV, which is like the estimate by the bounding chain on what are the block colors for the ghost chain, is S in the puzzle, and the block colors for Bob is TTV, which was T in our puzzle. So we shall ignore the other set GTV for now, because sort of complicates things, and we can talk about the main idea even without it. So let's just recall the puzzle. So you had this, now it's pretty clear, right? Alice is the bounding chain, and it has some estimate of what are the block colors for the ghost chain, and it needs to sort of think of a list of colors L, with L being as small as possible, such that there is a way the ghost chain can couple itself by using a color in L minus T. And why do you need this condition? This is the condition because you want the ghost chain to evolve according to the Glauber dynamics. So as long as you ensure that for all S and T, the distribution of C in this procedure is uniformly at random on K minus T, the ghost chain is happy. That's what the Glauber dynamics wanted it to do. And what we really want to do is minimize L, because if we minimize L, we are sort of proceeding towards coalescence. Right now, the solution suggested by Huber is like pretty much the trivial solution we saw, which is like you just sample a set of size delta plus 1 and give it to Bob, and it doesn't even take into account that there is, I mean, it doesn't really fully capture the fact that you have knowledge of S. But it's not exactly the same. There is some additional requirement, that is we need a non-trivial probability of producing a list of size 1. So this procedure that we are sort of suggesting should give Alice a chance of sometimes just sending across a list of size 1, right? That is important for us. So let me just tell you the solution of I'm almost out of time. I'll just take maybe 5 more minutes, and I have only 2 more slides. So let's see what we can do for the puzzle at least. So here's, I'm pretty sure some of you would have already figured it out, but here's one natural attempt. That is, why don't we just sample a color C1 in K minus S. So we sample this color. So this is what Alice is doing. She is sampling a color in K minus S and just sending across C1. So when Bob receives this list, there is only one color, so he has to output that. There is no other option. But this is not correct, because there is not enough mass on this band S minus T, right? So there is an easy way to remedy this. You just sort of sample again from S this time. Let's say you sample a color C2 from S, and you send across the list C1 comma C2, right? Now Bob has a choice of either using C1 or C2. Well, notice, at least by virtue of having C1 in our list, we know that Bob can always use some color which is not in T, right? So what does Bob do now? So Bob sort of does this kind of bias sampling trick. He just tosses a P biased coin. If it lands up heads, he just uses the color C1. And if it is tails, he will use C2 if it's possible, because sometimes it might not be possible to use C2. Alice doesn't know T. Otherwise, he'll again go back and use C1. If he can use C2, he'll use it, like in this case. Otherwise, he'll go and use C1 again, right? So I need to also sort of argue about the existence of this magical P. Like, why does it exist? So for P to exist, what do we really need? I mean, one way to think about is that you need to ensure that the amount of mass Bob puts on S minus T is the amount of mass he should have been putting on it. So if he were indeed sampling from K minus T, this is the amount of mass Bob would have put on S minus T, right? But according to our procedure, if Bob needs to produce something from S minus T, firstly the coin should land tails, so that's a 1 minus P, and on top of that, the next color should be in S minus T. So that's a probability of S minus T by S, because C2 is something which you sample from S, right? So this is just very simple equations, and if you rearrange it, you will get that what you really need is, for the existence of P, is that K is larger than mod S plus mod T, okay? And you can ensure this by requiring that you know that T is a set of size at most delta, because what was T? T was the block colors for the Glauber dynamics chain, but there are only delta neighbors at most. So you really want K to be larger than mod S plus delta for this procedure to work. Now Now this is not quite true, right? Because after the warm-up phase in Huber's chain, what you really have is that all the lists prescribed by the bounding chain are of size delta plus 1. To use the previous technique we just discussed, we need k to be larger than mod s plus delta. But after the warm-up, mod s, so what was mod s again? For every vertex, it's just the union of the colors in the bounding chain in its neighbors. It could be as large as either min of k or delta square plus delta, because there are delta neighbors each with potentially delta plus 1 list size. And you need delta more than that, so you will still be stuck with k being larger than delta square plus 2 delta. But as it turns out, you can sort of modify the warm-up to get around this procedure, and I've sort of skipped out a lot of details, but I mean, hopefully you will be enticed enough to read them in the paper. So we can sort of modify the chain a little bit, the warm-up part of it, and use this this sampling technique we discussed to actually obtain a bound of k equal to 4 delta. And if you sort of really go after the warm-up with more vigor, you can sort of get it down to 3 delta as well. And I should mention one thing, that this is not the way in which we obtained the results. Earlier we didn't quite get our hands on this warm-up. We were using Huber's warm-up, so we sort of had to play around with a lot of things and juggle them around to get a weaker bound of delta square by log delta. It is only later, like after a few months of leaving the problem, we realized that, oh, there is an easier warm-up chain which just gives you a 3 delta bound. So thank you. Thank you for listening. Yeah.
So the natural question, is this loss essential? Can you get down like 2 delta or even?
Yeah, so for our technique, 2 delta is like, we can show that using this kind of bounding chain approaches, you will never do better than 2 delta. And to get 2 delta is like the optimal thing these techniques can yield. But this extra delta factor really comes from the warm-up phase. If you can somehow get a warm-up phase which works with smaller values, then yeah, you will get, but we don't know how to get that. That's the reason, yeah.
So that's related to some list coloring number or something? This warm-up?
The warm-up actually, I mean, the reason why I need more than, why I need is this calculation for the existence of, so the warm-up actually also uses the same trick that we saw just now, the sampling trick. In that there is a calculation of the existence of P. So the existence of P really requires a gap of delta between the block colors, and so between the sets S and K there should be a gap of delta. Or if you are more careful, there should be a gap of size exactly T, because remember we got the bound K is greater than mod S plus mod T. To ensure that bound, you need to sort of lose this additional factor of delta over 2 delta. That's the reason I'm getting 3 delta right now. We are getting. But yeah, I am not making any special structural use of the graph, like its list, its chromatic number, or maybe its list coloring number is small or something.
All right, if there's no more questions, we can thank you so much.